Section 7.3, Mars, a victim of planetary freeze-drying. Our goals in this section are to look at the geologic features that tell us that water once flowed on Mars, and we want to see why or how Mars changed. So comparing Mars to Earth, we know that Mars is about 50% the Earth's radius and only about 10% Earth's mass. So it's much smaller and much lighter in mass. It's 1.5 AUs from the Sun compared to 1 AU for the Earth. Its axis tilt is about the same as Earth. It has a similar rotation period. It has a very thin carbon dioxide atmosphere. So although it's carbon dioxide, and we know that's a greenhouse gas, the amount of it is very, very small. So the main difference is Mars is a smaller planet. Here's what it looks like for the seasons of Mars. Again, looking at the tilt being very similar to what Earth has as far as a tilt toward or away from the sun, depending on the time of year. So the seasons on Mars being farther away from the sun are more extreme in the southern hemisphere because it has a more elliptical orbit. In other words, it's a little bit closer to the sun at one time of the year than on another. And you can see the same diagram on page 185. There are storms on Mars, dust storms. As you can see by the two photographs of the same area, this is between June and September of 2001. A dust storm occurred and pretty much browned out the surface of Mars for quite some time. So although the atmosphere is thin, it's dense enough that it can carry dust. This looks like some type of flow feature, river flow feature with possibly some sediment that's filled in what appears to be a river channel. The same pictures on page 188 of your textbook. So the surface of Mars appears to have these ancient riverbeds, these same U-shaped turns that the river takes. It's very similar to rivers that are on Earth. The conditions of craters indicate some sort of surface history. The craters on the left are partly eroded. The one on the right is very much eroded, possibly due to wind and water. Here's a map of the surface of Mars, same ones on page 186 of your book. This shows several of the landing sites that the United States has sent unmanned spacecraft to. So we have a pretty good idea of, based on what they did, what the surface structure of Mars is. In addition, there have been Mars orbiters, which have very well mapped the surface of Mars. Here's a volcano. It's called Olympus Mons. We think it's the largest volcano in our solar system. It's the statistics for it are in your book, but it's something that is very noticeable in a telescopic view of it. As you can see in the inset there, the crater is the product of volcanism, volcanic activity. So this is different from an impact crater. This is something that had been happening to the surface of Mars, and lava, of course, flowed out from that volcano. Here's what appears to be some sort of river channel formation near the equator of Mars, or some sort of tectonic activity. We're not really sure. There's these cracks in the surface of Mars that could have several different ways in which they formed. Here's where the rover, the lunar rover, the lunar spacecraft that landed on the surface, called Spirit and Opportunity, both of them being landers, discovered quite a bit of new information about the surface of Mars. And there's some pictures of what kinds of things these rovers have found on page 190. This is a good glimpse of what the Opportunity rover found in 2004, that there appears to have been a much, much larger amount of water, liquid water, on the surface of Mars in the past. So the question is, how could Mars have been warmer and wetter in the past? Here's more evidence of some sort of water action. We see on the left what appears to be a riverbed or gravel that water deposited, and on the right, a very similar formation on Earth. We're fairly certain that today most of the water lies underground, and it's frozen, obviously because of the low temperatures Mars experiences, but we think there is still water ice there. Some scientists believe the accumulated snowpack melts and then carves valleys even today. We see in the bottom part of this slide a crater with what appears to be a river delta, or technically what's called an alluvial fan, sitting inside the crater. Something like that on Earth is fairly common in arid regions out west. So why did Mars change? We see here the internal structure, the core, the mantle, and the crust of Mars. Mars has not had widespread surface water for about 3 billion years. That's at least the latest hypothesis. Scientists think the greenhouse effect probably kept the surface warmer before that. In other words, the amount of carbon dioxide and possibly other gases were much higher 3 billion years ago. And since then, Mars has lost a lot of that atmosphere. The same diagram on page 192 shows what may have happened. This solar wind may have actually pushed away a lot of these gases that would have otherwise kept Mars fairly warm and kept liquid water around. But because Mars is so small, it cooled faster. The core of Mars, which should have been something that would generate a magnetic field, basically froze in place. It no longer generated that field, and that allowed the solar wind to push away those essential gases. So the magnetic field may have preserved an early Martian atmosphere, but the solar wind may have stripped that atmosphere after it decreased because of interior cooling. The magnetic field decreased. So what geological features tell us that water once flowed on Mars? Well, there are dry riverbeds, there are eroded craters, rock-strewn floodplains, all showed that water once flowed on Mars. Today, Mars has ice, underground water ice, and perhaps pockets of underground liquid water. And as we just discovered this past week, we now know that there is a small amount of water flowing on the surface of Mars. Why did Mars change? Well, its atmosphere must have at one time been much thicker with its carbon dioxide and other gases, greenhouse gases, that kept the surface warmer and allowed liquid water to flow. But somehow Mars lost most of that atmosphere because of a declining magnetic field. Next, let's look at Venus, section 7.4, a hothouse world. So our goals here is to answer the question, is Venus geologically active? And why is Venus so hot? Well, as you can see by this picture, there are lots of features on the surface of Venus that tell us it has been very active in the past. This is the same picture as what you find on page 194. There's been some cratering on the surface of Venus. These are impact craters, but it appears there are fewer than the Moon or Mercury or even Mars. There's volcanoes on Mars, quite a few of them. So that would indicate that magma was coming up from the interior and spilling out in the form of lava and spreading out, forming these cones. There are fractures on the surface of Venus. So those fractures, being cracks or places where stress was relieved between parts of the crust, indicate that there was some kind of plate tectonics going on. Here's some photos of rocks taken by a Russian lander. The lander itself was able to survive for several minutes before it was basically crushed and melted by the extreme Venus atmosphere. So does Venus have plate tectonics? Well, most of the Earth's major geological features are attributed to plate tectonics, which gradually recycles or remakes the Earth's surface. But Venus doesn't appear to have any plate tectonics, but its entire surface seems to have been repaved a little less than 1 billion years ago. So maybe there was something going on, but it has also stopped. And next, why is Venus so hot? Well, the greenhouse effect on Venus keeps its surface to about 470 degrees Celsius. That's about 900 degrees Fahrenheit. But why is the greenhouse effect on Venus so much stronger than on Earth? Because it has a very thick carbon dioxide atmosphere, and so thick that the atmospheric pressure at the surface is 90 times that of Earth. So although Venus is about the same size as Earth, the amount of gases in its atmosphere is much, much higher, making the atmosphere much denser. So there's thick carbon dioxide in the atmosphere that produces a very, very strong greenhouse effect. And as we know, Venus is closer to the sun, so more of the sun's radiation can be absorbed. On the other hand, Earth escapes this fate because most of its carbon and water are in the rocks and the oceans. So the carbon in carbon dioxide recycles here on Earth. It doesn't recycle on Venus. The clouds contain droplets of sulfuric acid, which is obviously not a good thing if we were to visit there. And the upper atmosphere has some pretty fast winds that remain unexplained as far as why they blow. So some people call Venus having a runaway greenhouse effect. It would account for why Venus has so little water. Obviously, a temperature of 900 degrees would probably prevent much, if any, water to actually remain on the surface. So, is Venus geologically active? Well, its surface shows evidence of major volcanism and tectonics during the last billion years, but there's no evidence for erosion or plate tectonics beyond that. And why is Venus so hot? Well, the runaway greenhouse effect made Venus too hot for liquid oceans. Any water would have evaporated, and all the carbon dioxide remains in the atmosphere, leaving a huge greenhouse effect. Next, let's look at Earth. What unique features of Earth are important for human life? How is human activity changing our planet? And what makes a planet habitable? Well, here's a map of the Earth's surface, along with some of the ocean bottom features. We are sure that these motions are there because of GPS measurements, which can be very accurate. We know that these chunks of rock called plates are moving, as you see by the white arrows in those various directions. And of course, movement of plates or movement of huge pieces of crust are bound to cause problems or collisions or separations or sliding. So continents move just as ocean plates move. This idea was originally inspired by looking at continents like South America and Africa and seeing just how well the continents fit together. The mantle material erupts where the seafloor spreads out, and as we now know, of course, South America and Africa are very far apart. So something must have cut through that gap between the two and caused the continents to split. And this is the mechanism by which we think it's all happening. It's called seafloor recycling. At a place where continents are moving apart, such as between North America and Europe or South America and Africa, there is magma rising toward the surface. And eventually it comes up through what are called ridges. Mid-Atlantic Ridge is the example that's shown here. But there are other places where oceanic plate is diving below a continental plate, as you see on the left-hand side of the diagram. Those are called subduction zones. So the Earth isn't getting bigger or smaller, it's in balance. But it has to be in balance because where two plates might be spreading apart, forming new oceanic crust, there must be somewhere else where crust is being destroyed, such as along a subduction zone. So this diagram at the bottom of page 199 is a pretty important one. And this is a series of pictures that shows just how the continents have moved. And of course, the most recent movement began up over 200 million years ago. As you can see in the upper left, that's what we think the Earth's continents looked like at that time. And of course, since then, they have drifted apart. So as you can tell from the sequence here, the Atlantic Ocean has actually gotten bigger, but at the same time, the Pacific Ocean would have to get smaller. So even looking into the future, 150 million years from now, we can predict the movement of these plates. The Earth has something called a carbon dioxide cycle because of these movements of plates. We have atmospheric carbon dioxide dissolved in rainwater. The rain erodes the minerals that eventually flow into the ocean, and these minerals combine with carbon to make rocks on the ocean floor. I think most of us know of a rock called limestone. Limestone has a very high percentage of carbon. So let's say we have all of these sedimentary rocks which have formed on an ocean bottom. Step 4 shows that subduction carries the carbonate rocks down into the mantle. And then, number 5, the rock melts in the mantle and outgasses carbon dioxide, which comes back into the atmosphere through volcanic action. So we're looking at the diagram on page 200. So as far as long-term climate change, the changes in the Earth's axis tilt might lead to ice ages. Widespread ice tends to lower global temperatures by increasing the Earth's reflectivity, which makes sense. Ice and snow is white, so that will reflect more light. And CO2 from outgassing will build up if oceans are frozen, ultimately raising global temperatures again. So these climate changes are kind of interdependent, where one can cause another result. So plate tectonics creates climate stability, as it turns out. And climate stability allows liquid water to remain on the surface. Of course, liquid water is necessary for life, and life is necessary for atmospheric oxygen. The interplay between plants and animals, I think we all know. So how has human activity changed our planet? Well, based on this graph, we can see that in the last 40, 50 years, there's been a steady increase in the overall or global temperature. This is in degrees Celsius, but you still see a rise, even though the vertical axis there is showing in tenths of a degree Celsius. But the proof is there that the temperatures have been increasing, and we think it's due to human activity. We've done some things to our atmosphere that we shouldn't be proud of. Human-made CFCs, chlorofluorocarbons they're called, were put up into the atmosphere as the product of humans to put into spray cans and other aerosols. That destroys ozone, and of course destroying ozone reduces protection from ultraviolet radiation. Human activity is driving other species to extinction. And of course, human use of fossil fuels produces more greenhouse gas that can cause more global warming. So, Earth's average temperature we know has increased about 0.5 degree Celsius in the past 50 years. The concentration of CO2 is rising. And if those two things are happening, this unchecked rise in greenhouse gases will eventually lead to global warming. Of course, the term that's more popular today is climate change, but that change globally would appear to be a warmer Earth. These graphs show the concentration of CO2 that has been steadily increasing. And these same pictures are on page 202 of your book. So most of the CO2 increase has happened in the last 40 or 50 years. It's been plotted, we know it's happened, and now, of course, politicians around the world are starting to recognize it and try to or attempt to introduce legislation that might reduce those CO2 emissions. This is an interesting graph. It's on page 202 at the bottom. It shows what the difference is between what just regular solar and volcanic activity would do to our temperatures. That's the blue line. And what the red line is showing is just exactly what is happening due to human intervention. So we definitely have a correlation or a connection between what the rising temperature is doing and who's causing it. So what makes a planet habitable? In other words, what makes one planet livable and not the other? Well, any planet would have to be a certain distance from the sun for liquid water to exist. Too close and water would evaporate. Too far away, it would be frozen. The axis tilt, the interaction of continents, and of course the oceans would all play a part in that. But certainly the distance is the biggest factor. That distance being just right for us, about 93 million miles. These are pictures taken from page 206 of your book. What else makes a planet habitable? Well, it needs to be large enough for geological activity to release and retain water and have an atmosphere. So the smaller terrestrial planets would not have an atmosphere because there's nothing to protect the atmosphere from the solar wind blowing it away. So the same picture that you see on page 207 is here, which says the Earth is habitable because it's large enough to remain geologically active, it's the right distance from the sun, so oceans could actually form and stay. Any other combination of factors would probably not produce a planet that had water in a liquid form. So what unique features of Earth are important for life? Well, certainly liquid water, atmospheric oxygen in order for animals to survive, certainly. Plate tectonics, and that is definitely something that's active on our planet. And climate stability, which is in question right now, knowing that the amount of greenhouse gases is increasing and we see climate changing, that stability may be in danger. So how is human activity changing our planet? Well, it's releasing carbon dioxide into the Earth's atmosphere, it's increasing the greenhouse effect, and it is producing global warming. What makes a planet habitable? Well, the Earth's distance from the sun allows for liquid water on the Earth's surface, and Earth's size allows it to retain an atmosphere and enough internal heat to drive geological activity. So it's in a lot of ways the geology or the internal structure of the planet that has quite a bit to do with just whether a planet would be habitable.